And we're back. Welcome back from the weekend. Today, we will continue on with our discussion of conditional probability with Bayes' rule. Before we begin, a few administrative bits. The reading by the 17th in Barron Chapter 2, Section 2.4, that's pages 26 through 32. It's not a lot. Please make sure you are doing work every day for this class, at least an hour a day. Study hard, study like a ninja, and read every single day. Project 1 is due on the 15th. That would be this evening at the usual 1 second before midnight at 11:59 and 59 seconds p.m. Please make sure you plan your time accordingly. Do not wait to the last minute, and make sure what you're handing in will run. Projects that do not run receive a 0 without review. Okay, so where we left off, we talked about this idea of so-called filtering probabilities or conditional probabilities, and we said that when we calculate a conditional probability, we are changing the so-called universe of consideration, and that would refer to the denominator of our scheme for how you actually calculate a probability. In the example we gave, we had a bunch of balls, and they were labeled with a number depicting the bin from which each ball originated. So we have balls labeled 1 for bin 1, balls labeled 3 for bin 3, balls labeled 5, and balls with a label of 7. In addition, the balls have a color, and that color is either green or yellow. And so in the example we gave, we said, what would the probability be of picking a ball if all these balls were emptied into a bin whose color is green, given that you knew only the contents of bin 5 were emptied in? So what this does is it changes the universe of consideration from all 20 balls to just the 5 balls that are in bin 5. Moreover, then when we compute for all those balls in bin 5, the probability of green, we're counting 1, 2 greens out of a total number of 5 for a probability of 2/5. We also took a different look based on the Venn diagram at what the calculation is for conditional probability. And this expression is how you relate the conditional probability of A given B to the probabilities of the A and B events. And so we take the overlap region between A and B, that's what's common, that's the favorable outcomes. So both A and B events are true. That's the intersect overlap region. And we divide by that probability of B, which is that shaded region in the Venn diagram corresponding to B. Okay, so let's continue on with Bayes' rule. And here's our definition of conditional probability. And when we write that definition, first let me select my pen color. I'm going to select blue this time. We have our definition from before for probability of A given B is a probability of A and B divided by probability of B. We also write the probability of B given A as a probability of B and A over the probability of A. Now, we know that the and is commutative, right? And by commutative, I mean that the probability of A and B is the same as the probability of B and A. It's just a helpful thing when you're writing out the definition for conditional probability to write the B and the A, or the variables, in the and portion and the numerator for the definition, to write it in the same order from left to right as the probability of that variable and the condition. So here we have B given A, so we have B followed by A. Here we have A given B, so we have A and B. It just kind of helps out to remember how you write it. But please do remember that the and is the same. So we could actually write this probability of B given A as a numerator equally as valid as saying probability of A and B over probability of A. But I choose to write it this way because it's sort of reminiscent, if you will, a great memory device mnemonic for remembering if I have B given A, it's B and A. Okay, so we have our conditional probabilities, and we know that the and is commutative. So we're going to take advantage of this fact that and is commutative, and we're going to write the numerator in both the probability of A given B and the probability of B given A expansions. We're going to write those numerators the same way, right? So we know the and is commutative, so we write probability of B given A as probability of A ANDed with B over probability of A, okay? And then we also write probability of A given B. That's A and B over probability of B. So now, if we take a look at this, we have our two expressions. Let's do a little bit of some algebra. So we're going to multiply, in the case of our expression on the left-hand side, we're going to multiply both sides of equality by the expression probability of A. Okay, so if I do that, what do I observe? Well, I see I have a probability of A in the numerator. I have a probability of A in the denominator. Well, these cancel, goes to 1. And I'm left with probability of B, and I almost forgot, I multiply both sides. If I multiply the right-hand side by probability of A, I also multiply the left-hand side by probability of A. So what I'm left with when I cancel my probability of A on the right-hand side in the numerator and denominator, I'm left with the following expression. I have probability of B and A times probability of A on the left-hand side of equality, and then I have probability of A and B on the right-hand side of equality. Likewise, for the expansion for conditional probability of A given B, I'm going to multiply both sides of equality by probability of B. So I multiply by probability of B on the right-hand side of equality, and likewise I multiply by probability of B on the left-hand side of equality. Now again, we see in both the numerator and denominator, we have probability of B on the right-hand side. So these cancel, goes to 1, and I'm left with probability of A given B times probability of B is equal to probability of A and B. Okay, so if we take a look at this, we have two different definitions for what is equal to probability of A and B. Likewise, if we're going to write this left to right, we'd say probability of A and B is equal to probability of B given A times probability of B. And I'm just writing that the other direction from right to left because equality is commutative. It doesn't matter if I have one term on the left-hand side of equality or right-hand side of equality. Likewise, if I expanded probability of A and B using the second approach, I get probability of A and B is equal to probability of A given B times the probability of B. So what do we have here? We have two different expansions for what it means to be equal to probability of A given B. I have this version, B given A times probability of B, and I have that version, probability of A given B times probability of B. So if they're both equal to A and B, this intersection, I can certainly equate together these two expressions on the right-hand side of equality. They're both equal to the same thing. Well, A and B is equal to A and B, so the right-hand sides are equal to one another. Okay, so this term here that I've expanded, that has a name. It's called the product rule. And what the product rule does, it defines, in terms of conditional probability, what it means to have this overlap region, probability of A intersect B for two events. Okay, so we equate then these two expansions, these two different versions of the product rule. Here's my first version of the product rule for expanding out what A intersect B is. That's probability of B given A times probability of A. I have that on the right-hand side. And then I have my other expansion of A intersect B, probability of. That's probability of A given B times probability of B. That's what I have on the right-hand side. So I equate the two together because these two product rules are equal to the same quantity, so I can equate them to get to one another. So I do this equating of them to one another, and I then do a little bit more algebra. I'm going to take my expression, and I'm going to divide both sides of equality by probability of A. So I divide the left-hand side by probability of A, and I also divide the right-hand side of equality by probability of A. Okay, so if I look at the left-hand side of equality, I see that I have a probability of A in the numerator, and I have probability of A in the denominator. Of course, that goes to 1, cancels, and I'm left with probability of B given A is equal to probability of A given B times the probability of B upon probability of A. Okay, so this expression has a name. It's called Bayes' rule. And Bayes' rule is really, really important in probability and so-called Bayesian probability. We said that a conditional probability allows you to consider how chances change in light of new information. You can also scenario test what happens if I got this type of new information. This Bayes' rule connects two different expressions involving different conditions, namely this idea of given A to given B. And this is very useful in cases where you have one piece of information, but you want to evaluate a probabilistic question concerning a different piece of information where you don't really have that different piece of information. Now, this is used all over machine learning and classification, robotic clustering, all sorts of applications. So let's use an example, and this example is from the book. Now, in the statement from the book, you have 90% of flights depart on time. That's the event D corresponding to a flight departing on time. You also have 80% of flights that arrive on time. That's this event A, arrival on time. And then you also have 75% of the flights both depart on time and arrive on time. So that would be, if you think about what that and means, it would mean that the probability of this arrival event and at the same time the departure event was true, that's equal to 75%. So if we do this or express this in mathematical notation, we get probability of A, arrival, is 0.8 for 80%. Probability of D, event D, for departure on time is 90%, 0.9. And lastly, the probability of A and D, arrival and departure both being on time, that would be 75% or 0.75. Okay, so now what if we wanted to calculate the probability of an arrival on time for the plane, given that it departed on time? Well, let's just do the expansion for conditional probability. So that's probability of A given D is equal to probability of A and D over probability of D. That's just our definition of conditional probability. So then we plug in our numbers. That's A and D, it's 0.75 divided by probability of D, that's over 0.9. That's 83.33%, or 0.8333. Likewise, if we were to evaluate the opposite condition, probability that you departed on time, given that you arrived on time, well, we just do the expansion once again of Bayes' rule. That's probability of D and A over probability of A. And this D and A is the same as A and D, which we said was 0.75 probability. Okay, that's in our numerator. And the denominator, probability of A, from the problem specification was 0.8 or 80%. We do the math on that, do a little bit of algebra, and that is 93.75% or 0.9375. So those are our numbers. Now what we're going to do then is we're going to evaluate probability of D given A using our Bayes rule and show that you get the same expression. So let's say, for example, you wanted to know the probability of D, the departure, given that it arrived on time, but you don't have an observation or new information about arrival on time. Well, if we use Bayes' rule, let's look at what happens. So we're not given the arrival on time, but we do know about the departure. So we apply Bayes' rule, probability of D given A is equal to A given D times probability of D divided by probability of A. So we have an expression for A given D, right? That probability we said at the outset was 0.8333. So we plug that in. We multiply that conditional times probability of D. Well, we know probability of D is 0.9. And then we divide that by probability of A. Well, that's 0.8 from the specification. Lo and behold, we get the same result. We get this 0.9375, which is 93.75%. And so what this allows us to do, when we say given, it means that you observe that this particular thing is true. But what if you don't have that observation? You can synthesize as if you could observe that arrival given A using this expansion, our Bayes rule. Okay, so it allows you to be able to evaluate conditions without ever having had an observation for something. A really powerful mechanism that's used in a number of ways in machine learning. Okay, so rather than requiring an observation that's given A, we can construct it using other observations that's given D, and you might just have this observation given D. All right, so let's take a look at this last part. And this total probability is a decomposition that allows you to talk about constructing a probability using a number of non-overlapping or disjoint events. So I'm going to take a little bit of time to explain this diagram. Suppose we have our sample space omega, the set of all possible observables that we can have. Now, this sample space we are going to draw as being almost like a Sicilian pizza, right? You cut it into little squares. And each slice is going to be non-overlapping. We have slice B1, we have slice B2, we have slice B3, slice B4, slice B5, slice B6, and so forth. And so when we refer to any arbitrary slice here, we're going to represent an arbitrary slice as the ith slice here, Bi, or the jth slice down here, which is Bj. And it just so happens I is not equal to j because the arbitrary ith slice is not the same index as this jth slice. So that's the approach we're going to use to talk about this idea of two different slices in this partitioning or cutting up into non-overlapping pieces, this cutting up of the sample space omega. Now, how many slices do we have? We have k many slices. And it doesn't really matter what k is. In this particular case, k is 24 because we have 24 slices, but k can be anything. We haven't set a restriction on k. Now, it just so happens we partition this. An observation to make about this partition is that none of these bi slices overlap with one another. That means if you're going to take the intersection between an ith slice and a jth slice, that's going to be the empty set. And by definition of non-overlapping in the Venn diagram, it means they do not share elements, and therefore the intersection is empty. And so if we draw some other event A, you'll notice here parts of A are in some slices, but not other slices. And moreover, if we were to kind of take A as it is partitioned up by each of these non-overlapping slices, what do we get? Well, we get a piece of A up top like that. We get a piece of A that's full like that. We get a piece of A on the side that's kind of like this. We get another piece of A that's the dual of that, like this. And then we get another piece of A like this. And another piece of A like that. And then we get this tiny little sliver on top. And then we get another square right here closer to the center. And so if we look at each one of these pieces, together they form that event that we're calling A. And so A is effectively cut up into slices or into pieces by each one of these B slices. And because each one of these B slices do not overlap, the intersection is null, it means that we can construct A in a clever way by just putting together all those parts of A that happen to be in one of these B slices. Okay, so each of these B slices, if we take the union of them, that comprises or composes our sample space omega. That means they're collectively exhaustive, something we talked about in a previous module. Likewise, for any two of these slices, Bi and Bj, their intersection is null. That means they're mutually exclusive, or pairwise independent. And we talked about that at a previous module. And so all of these B slices, because they're mutually exclusive and collectively exhaustive, we can use them in a clever way to construct any event A. Now, this goes back to our definition about what it means to be a probability. We had this idea called sigma additivity. Sigma additivity. And what that said is that if you have a set of non-overlapping events and you want to compute the probability of the union of those pairwise disjoint events, that probability of the complex event constructed from such a union is going to be the sum of the individual probabilities. So if we take our A event, we can construct A by taking the union together of those pieces of A that intersect with this slice, with this slice, with this slice, with this slice, this slice, this slice, this slice, and this slice. And when we do that, we know that because we intersect A with each one of these slices, together each one of those individual B slice intersections is going to be independent from all the other B slice intersections. So that means we can construct A as a disjoint collection of simpler events, and we're guaranteed that each one of those pieces will not intersect with one another because the original B slice partitioning, they do not intersect with one another. So we take A and we intersect it with our first B slice, and then we take A, intersect it with our second, up to and including our kth B slice. Each one of these results is going to be pairwise independent. And now we take the union of each one of those B slice intersections, and that gives us our original set A. So with this idea of these disjoint B slice partitioning of our sample space omega, we can force the breaking apart of any event A, and we have now a method for constructing this probability of this complex event A, regardless of what its contents originally were. And so if we were to calculate then from this the probability of A, well, that's nothing more than the probability of the first intersection, A intersect B1, plus the probability of the second intersection, A intersect B2 for the second B slice, plus all the way to the sum, plus probability of A with that last B slice partition. And you can do this again because each one of these intersections is pairwise independent or mutually exclusive of all the other B slice partitions. And so with that, and we talked about this property before, we can take advantage of sigma additivity, and we can say the probability of A, our complex event, is nothing more than the sum of all of the simpler events. Okay, where the simpler events are probability of A intersect with each one of the B slice partitions. And we sum over all the K many B slice partitions. All right, so we can decompose the probability of a complex event into the sum of a number of disjoint events, and we can force those pieces to be disjoint by intersecting our original complex event with a number of partitions, each one of which are non-overlapping, i.e. they are disjoint. Okay, and so this is our expression for this decomposition of complex event A into a number of disjoint pieces. And we call this a partitioning of event A. And we can now take this expression for what A and B is for each B slice partition, and we can apply the product rule that we had just discussed earlier. So in doing so, we get then probability of A is just the sum of disjoint parts, and those disjoint parts are these B slice intersections. And because that's an anding between two events, that's just the probability of A given that jth B slice times the probability of that jth B slice. This is just an application of the product rule. that we talked about before. So this expression has a name. It's called the sum rule, and it describes how you construct the probability of an event from a number of disjoint pieces. And we force or induce these disjoint pieces by intersecting A with a number of disjoint partitions, our so-called B-slice partitions in this example. Okay, and so if we had two B-slice partitions, how would we draw that in the Venn diagram? Well, here we have event A, and let's say A straddles two of the B-slice partitions. We'll call that B, and we call the other part not B. We could call it B1 and B2, or B and not B. Now, I call it not B because it's only two of them. Everything that's outside of B event is not B. So if we want the probability then of A, well, we plug in for K equals 2 in this example. That's the probability of A is A given B times the probability of the first piece, that's B, plus the probability of A given the second piece, that's B bar, times probability of the second piece, which is B bar. Right? So this is a direct application of the sum rule where the number of B-slice partitions is equal to 2. So K equals 2 in this case. So we can make use of this, and we can actually take these factors in this decomposition for the probability of A given B times probability of B, probability of A given B bar times probability of B bar, and we can apply the sum rule. If we do that sum rule, we get A intersect B in the first case, and in the second term, we get A intersect not B. And again, this is just the same thing from before, our sum rule, but we are making use of the product rule to change those terms within that two-term expansion for what it means to be probability of A. Okay, so if we rewrite Bayes' rule, we can make use of this sigma additivity using the sum rule, and we can actually change the denominator, and something very interesting happens. And so with this, we have probability of B given A is equal to probability A given B times probability of B over this sum rule, this two-way sum rule. Probability of A given B times probability of B plus probability of A given B bar times probability of B bar. So you might be asking, well, how exactly did we get this? Let's take a look at it. We know that probability of B given A is probability of A and B over probability of A, right? That's our conditional probability. We can take our product rule and we can change the numerator to be probability of A given B times probability of B. That's just an application of the product rule. We're making this substitution with that term. That's just product rule. Product rule. Okay. So if we look at the denominator, you'll notice we have a probability of A. Well, what is the probability of A? We will substitute the sum rule. The sum rule says the probability of A is nothing more than the sum of the probability of A intersected with each one of the B slices for however many B slices that we have. Okay, so let's assume we had two B slices. Well, we'll take our definition for this disjoint set of B slices intersected with A, and we can apply the product rule to that intersection. So apply the product rule, and we get this term, right? That's just a replacement using the product rule. Okay, so now we take that replacement using the product rule, and we just rewrite it, and now we'll expand it out based on a K equals 2 assumption that we had from before. So if we had two B slices, so here if K is equal to 2, and that's the scenario where you have B and not B, and you have some event A, and maybe A straddles both, and maybe A doesn't straddle both. So it doesn't matter where A is in this Venn diagram. It's the same result. And so now we substitute and we expand out using this particular sum rule that we talked about before for K equals 2, and we just replace this sigma notation for the sum rule with this written out expanded version for K equals 2. And we get in the denominator probability of A given B times probability of B plus probability of A given B bar times probability of B. Okay. And so one of the things that you'll notice here is that in this expansion, this is also Bayes' rule, probability of B given A is given A, and you'll notice for the expression on the right-hand side, anytime we make an observation given, it's always given something with B. That's given B. Here we have given B. Here we have given B prime. And so we're again synthesizing what it means for the probability of B given that I have observed A, but if I don't have an observation, I can express that same quantity, that same probability, if I know I have observations of B and therefore observations of B prime, because I can get B bar by saying 1 minus B, right? I can calculate that easily. Okay, so with this version of Bayes' rule, the interesting part is I may never observe A, but I can still evaluate the probability or a probability as if I observed A, as long as I have, in this case, an observation involving B and B bar. Okay, so with that, let's move on to Matlab. We're going to have a little bit of instruction about subplots and subfigures in Matlab. Okay. So here we're in the Matlab. I've created a script, test subplot, and I'm going to begin, set an image. I'm going to read an image, I am read. I'm going to give it the name of an image to read, and I'm going to call it image name. And for image name, I've preloaded an image or copied an image up to my directory, and it's called a dog's life.jpg. Okay, so I have a dog's life.jpg, and I'm going to read this in to my workspace. So I am read image name, and then I'm going to plot this image, and the special way to plot it is to show the image. So I am show that image I, and it's a color image. Okay, so if I save this, I run it, okay, well, we see that the image pops up, and I get this beautiful color image of this dog that has just a great life. Riding on a boat, lazy afternoon, the sun is up, the sky is blue, it's just lovely, you're on the water. Nothing like this dog just has a great life. Okay, so we're going to now take this and going to do some operations on it. But before we show the image, we're going to put it in a figure. So I'm going to label that figure, figure 1, and that's how you create different figures that you can show. So I could say figure 1, show that image. And what if I wanted to create a gray version of the image? The gray version, red, green, blue, to gray for that image. And so if I wanted to show the gray version, I'd say figure 2 to name a second figure, and I am show the grayscale version, IG. Okay, so if I do that, and I'm gonna my habit is to say display done, so that I have an executable statement on which to set a breakpoint at the end, and also it tells me that my program is done executing. All right, so if I run this, we'll notice that, of course, I have two figures that pop up. I have figure 1, and I have figure 2. Okay, but what happens if sometimes I want to be able to plot things side by side, right? If I have a number of things that I want to be able to show. Well, there's something called subfigure, and subfigure or subplot. There, so you'll see. Let me just make sure I help subplot. Subplot allows you to refer to the same image, and it's tiled into some number of rows, some number of columns. And so in this, suppose I wanted a 1-row, 2-column figure, I could just, instead of creating a separate figure for each one, put them all in the same figure, but divide that figure into regions and then show each one. Okay, so let's do this. And we have figure 1. We have a single figure, and I'm going to create the grayscale version of the image up top along with the color that I read in. And I'm going to have a single image, and I'm going to show the color image and the grayscale image. So now I'm going to say subplot, and when I subplot, I'm going to say the number of rows. So it's going to be 1 row, 2 columns, and I want to refer to the first cell. So if I say this first number 1, second number 2, that's the number of rows, number of columns, and then which one I'm referring to, which image. Now, of course, if I had 2 by 2, well, my going from left to right, top to bottom, I would have image number 1, image number 2, image number 3, image number 4 in a 2 by 2. And so here, when I say subplot 1, 2, I say plot in a 1 by 2 cutting up of figure 1. The first image is going to be this result of IM show. So then, if I want to display the grayscale image, I would say subplot in that 1 by 2 cutting up of the figure number 1, second image, and it's going to plot the grayscale. So let's take a look at this and see what our result is. So now if we look at this, we notice that we take our figure 1, and figure 1 is divided into 1 row, 1, 2 columns, and the IM show for the color happened in the first position, and the IM show for the grayscale happened in the second position. So let's see what happens if we change this. Instead of saying 1 by 2, what if we said 2 by 2, and this is 2 by 2, plot the first cell and plot, say, the third cell. Okay, so the third cell. And remember how we labeled, how we traverse the cells is top to bottom, left to right. So if I run this and we look at this, well, what happens? We take the figure, we chop it up into 2 by 2. So it's 1, 2 rows, 1, 2 columns. The first cell is here, the second cell is here, the third cell is here, and the fourth cell is there. So we can actually, if we decide to change this to the fourth cell, we see what happens. We're going to have images along the diagonals in the resulting chopping up of 2 by 2 for this figure. And so we have figure 1. The first cell has the color. The second cell is empty. The third cell has nothing. And the fourth cell has color. So let's try out putting something in the other regions. So let's take a look at IM hist, histogram of 3D intensity image. So let's take a look at IM hist and see what that gives us. And we're going to put that subplot 2 by 2, the second cell, and the second cell we're going to do IM hist of the RGB image. Okay, so let's see what we get here. So if we do that, oops, we have a little, oops, I misspelled it, subplot. It should be subplot. It's a problem with computers. They do exactly what you tell them to. All right, so let's take a look at this. And so here, you'll notice here, in the first cell, second cell, third cell, fourth cell, we have nothing in the third cell, right? So this is what subplot does. It allows you to have multiple figures in the same, multiple images or multiple plots or displays in the same figure. And subplot takes the approach of carving up your figure into number of rows, number of columns. That's that first numbers, number of rows, second numbers, number of columns, and then you have individual numbers for referring to the particular cells. And so with this, you can have a nice compact display. For example, if you want to show some report or some histogram, in this case, that depicts information in that image, you can actually put them side by side or top and bottom or what have you. Okay, so let's go back to Matlab. Let's go back to the PowerPoint. And we're back to PowerPoint, and that is another small installment of some Matlab isms that will be important throughout the semester. So with that, I'll end there, and I look forward to your Project 1s due this evening, Tuesday, September 15th, at the usual 1 second before midnight, 11:59 and 59 seconds p.m., and make sure you read every day, study like a ninja. So with that, we'll end there, and as always, stay healthy, Stay safe, and I will see you Thursday.